So basically Absint provides development tools for embedded systems, and our focus really is on tools for verification, validation, and also certification of safety critical software, increasingly also for security relevant software. The company is now more than 25 years old. We have about 40 to 50 employees, and our customers essentially come from all over the world with industries, all kinds of industry related to any safety or security relevant requirements. So of course that's aerospace, that's automotive, railway, energy, be it nuclear power or wind energy, and also medical products.
Okay, sorry to interrupt you, Daniel. You are sharing the speaker screen, not the
so it's the wrong one after all. Okay, then let's just switch. Better now?
Yeah, good.
So, yes, good that you mentioned it. All right. So we have a couple of products in the field. The first three are in the area of real-time software. So with the first one here, AIT worst-case execution time analyzer, the goal is to compute timing guarantees on timing predictable processors, or to be more precise, worst-case execution time guarantees. So you want to make sure that each task terminates inside its deadline. The time weaver then computes worst-case execution time bounds for high-performance multi-core processors, again at the task level. And with the timing profiler, the goal is to make worst-case execution time estimations early in the development process. So you can become aware of timing defects while you're developing the software, and in particular if you're doing model-based software. Well, stack analyzer, as the name already says, here the goal is to prove the absence of stack overflows. Then we have a tool which is not a static analysis tool, but again a formal methods tool. It's the ComCert compiler, which is basically the only formally verified optimizing C compiler which is on the market today. And then we have another static analyzer, this time working at the C code level or C++ code level, that's Astray. And here the goal is to analyze the source code for runtime errors, data races and other defects, and to check coding guidelines. So much for the introduction. Now let's have a look at some trends which are visible on the market today. Let's first look at safety critical systems. So in safety critical systems you can observe that there is an increasing connectivity. So safety critical systems which were closed in the old days are increasingly opening up. So there are cloud-based services, X-to-X communication, over-the-air updates, applications like smart mobility, smart grid, which makes which incurs the danger of making these systems also vulnerable to cybersecurity attacks. And actually this is something you can observe. So there is an increasing frequency of cybersecurity issues, and also there is a danger that the attack scale is really growing. So that means we have increasing connectivity. At the same time we have increasing complexity, driven to a big degree by, let's say, the trend to more and more autonomous systems like highly automatic driving, unmanned aerial vehicles, robotics, smart medical devices, and so on. And then with a growing data cloud, there are also increasing privacy concerns because more and more critical data are also shared in some devices. So that means overall, even if you look at safety critical system, there is an increasing list of increasingly critical software defects. But of course the question of software quality is not just constrained to safety critical systems. So this here is a quite interesting study from 5 to 6 years ago, and they said, okay, if you just look in the US and just look in 2018, the cost of poor software quality is about 2.84 trillion US dollars, which is quite a lot. So it's an interesting study to read. The outcome, or one of the conclusion is, well, the idea is if you want to reduce this cost, is to fix and find problems as early as possible. And then of course they drill down a bit, so they divide certain losses from certain in certain areas. So one is just direct losses, one is the cost of finding or fixing defects, and so on. So there are more studies also in this field, but some more numbers here on this slide, which contribute to the slide essentially before, or related figures as well. If you look at projects, a significant amount of project doesn't successfully terminate. So which means either it overshoots time or budget, or is completely cancelled. And then a factor also often neglected is software maintenance. So if you look at the maintenance costs, that's a significant amount of the overall software development cost coming from the same study. And this is also things like repairing bugs, shipping updates, and essentially dealing with technical debts. And then of course, so this is basically internal costs, and then of course there can be external costs, like if there are accidental injuries in safety systems, if there are recalls, or if there are lawsuits or liability claims. Okay. There is another book which is quite interesting to read, The Economics of Software Quality, which tries to give some numbers to software development properties, including software defects. And this is a screenshot from the book, basically showing costs of certain software defects in certain domains. You can see, okay, it's not just systems and embedded software, but also more general software. And well, the insights you can gain from this table is that, well, there are some software defects which are actually very expensive, and well, they do happen. And some of those very expensive examples which went through all the media are listed here. Well, let's say, for example, the Toyota braking problem, the unintended acceleration, the Ariane 5 issue, Terrac 25 issue, Patriot missile rounding errors, the Yorktown destroyer, and also F-35 crash this year. Okay. The trouble is that in advance you don't really know what the cost of a software defect would be. So let's say the conservative approach would be to make sure that you don't have bugs at all. And this leads to basically defect prevention methods. And that's also an overview from the book I just cited. So they compare certain defect prevention methods and rate them for, let's say, their potential, their effectiveness. And what you can see here is that actually static analysis of source code ranks pretty high in this table, close to things like, well, risk analysis, prototyping, or reuse of certified components. So from a methodological perspective, it's basically the highest one you find here. And that's just unsound static analysis. I'll talk a bit more about this later. So that means that, well, in terms of, on this slide, the effectiveness of defect prevention, and on this slide also the effectiveness of defect removal, there again, static analysis is ranked pretty high. Here it's on place 3. So you can see, if you just look at this book, static analysis somehow is ranked pretty high. Okay, and in this talk I also try to give an overview a bit more about why this is the case and what aspects do we have to take into account. First, let's maybe start with safety, because there is a clear introduction or a clear contribution where static analysis really helps. If you look at any safety norm which is around, it's clear that you have to demonstrate the functional safety of the software, which first means that you have to show its functional correctness. And well, that means you have to show that the functional requirements are met, and typically for this you use some testing methods, sometimes also formal methods. And you can see that all these safety norms also require to take into account certain safety relevant quality requirements, in the old days termed non-functional requirements, because they were not specific to a particular function. Instead, they more or less universally apply. Like, for example, the software should not crash because of runtime errors, like division by zero, buffer overflows, numeric overflows, all kinds of other pointer problems. There is a topic of resource usage. If you have a real-time system, the reactions should occur in time. You do not want the system to crash with a stack overflow. Then there is the topic of multi-threaded execution. If you have multiple threads of execution, you do not want to have one thread destroying data of another thread or to interfere on reading or writing data in an unexpected way. Then whether the source code really complies with the software architecture is an interesting question, and whether during integration tests you really exerted the interactions between the software components which really happen to a sufficient degree. So that's all kinds, all of these are examples of these more general quality requirements. The trouble is that here you cannot really proceed well with tests and measurements. You cannot just write a specific test case, please trigger my maximal stack usage. It's unclear when that happens. So you can just do unfocused testing, and the test end criteria are also unclear because all these properties are basically path properties, and you will never achieve full path coverage during any kind of realistic testing of a system. Okay, and it turns out that for these properties, static analysis is very well suited. You can address all of these topics with static analysis, and if you use the formal technique of static analysis, the abstract interpretation, you can even make sure that really no defect is missed. Okay, and an interesting observation also is that some of these issues here are also security relevant. So there is an overlap between the safety and the security process, and you will find the corresponding requirements or objectives also in norms like the ISO 21434 or DO 356A, like buffer overflows, uninitialized variables, data races. Right, so the contribution of static analysis is not just code guideline checking. It's much more. So it includes, of course, the code guideline checking, computation of code metrics, but also runtime error analysis, data and control flow analysis, data and control coupling analysis, and also basically hardware-related topics like worst-case execution time analysis or stack usage analysis. Okay, let's take a brief look into cybersecurity again. So if you take the classical definition of cybersecurity or security, it means you have to observe the CIA principle: confidentiality, integrity, availability. And when you look close at this, you can see that, well, if you have a safety system, all of these aspects are also safety relevant. Confidentiality. So basically, if you, for example, leak a maintenance or administrator password, well, of course, this can have safety relevant effects. Integrity is obvious. If data could be modified in an unauthorized or undetected way, well, then of course this can be safety relevant. And availability also is obvious. If certain parts of the system are not accessible anymore, that can be a safety issue. So basically all these security aspects also can have an impact on safety. And what you can definitely say is that there are some safety properties, if they are violated, then the system will not be secure, and vice versa. So if some cybersecurity properties are violated, then the system will not be safe. So you can't just say, okay, if the system is not secure, it will not be safe, and vice versa. It's a bit more fine-grained than that, but there definitely is an interdependence. And when looking at systems, then basically the relation between safety and security needs to be investigated. So if the safety and the security goals align, that's fine. But when there is a conflict, these conflicts have to be resolved. Like, for example, here in DO 356A, so in doubt, well, if you have to decide between fail-safe or fail-secure, well, then fail-safe takes precedence. So that's about the relation between safety and security. And from the security perspective, this is quite an interesting web page from the American CISA. And, well, they said, okay, if you look at past vulnerabilities at the software level, then, well, many of them are related to runtime errors like buffer overflows, and in particular buffer overflows on the stack or on the heap. And they actually termed this unforgivable defects. So that's pretty strong language. And it means that basically the well, these kinds of software defects are also in the public perception, even outside classical safety systems, are becoming less and less accepted. Interesting as well is this White House report, Back to the Building Blocks, the path towards secure and measurable software. And again, they said, well, if you look at many current cybersecurity issues, so here you find the text here, well, actually, they were caused by memory safety issues. So that also shows the relation between cybersecurity and safety. So there is definitely a relation. And they said, okay, well, either then you could use a memory-safe language, which most people don't, or, and it is also important that there is no memory safety language as such. You also have to use it in a memory-safe way. Or you can use formal methods like, for example, sound static analysis. So you can see, okay, static analysis is even something mentioned by the White House in the US. All right, so then let's have a look what static analysis really is. Well, the definition is that it's a technique which allows you to compute results about the software without actually executing it. Okay, and then depending on the depth at which you look at the software, you can distinguish different levels. The easiest one is the syntax. So, for example, if you look at the MISRA norms, on purpose, a lot of the rules have been just formulated on the syntax because it makes them easy to check, easy to follow. But in the end, the question always is, well, do I have an error in this program at this location, yes or no? And this is, of course, a question about the semantics. And the bad news is that, well, this is an undecidable problem, so there cannot be a tool which gives a correct yes or no answer in all possible cases. So it's the undecidability problem. It's just not possible. It can always happen that, well, the tool might report a false positive. So yes, it says, you have a problem there, but you don't, actually. Or the worst case even is a false negative, that the tool says, I don't find anything, there is no defect here, but there is. And then you can approach semantics-based questions at two levels. The easy one is the unsound level. So there you can find bug hunters, bug finders. There are many tools in this area which can have false positives and false negatives. And you can use the formal method of static analysis, abstract interpretation, where you can essentially prove soundness of the analysis. And soundness means that, well, there will be no defect missed. So here you cannot have false negatives anymore. For runtime error analysis, that means that, for example, no buffer overflow is missed. For worst case execution time or worst case stack usage, it means that the true worst case is never underestimated, it can just be overestimated. Okay, now let's look at safety norms again, because there it's nice to basically track the corresponding requirements. So one observation is of the DO that verification is not just testing, because with testing you can find bugs, but you cannot show the absence of errors. And then there is the formal method supplement, DO 333 to DO 178C, which, for example, also counts abstract interpretation among the formal methods and also introduces it. I have that on the next slide. With respect to the requirements you can access by static analysis, one example is the accuracy and consistency objective at the source code level. And here, well, you have to determine correctness and consistency. You have to look at things like stack usage, memory usage, overflows, so that means runtime errors, worst case execution time, uninitialized variables, so runtime errors again, data corruption due to task interrupt conflicts, worst case execution time. So basically you will find all these topics I've mentioned before in this objective. Now abstract interpretation is a formal method Well, and the general idea is that if you want to analyze big software, you need to make abstractions, like for example talking about intervals instead of enumerating all possible values. And when doing abstractions, there is always the danger of doing it wrong. So the idea of abstract interpretation is to have a formalism where you can prove your abstractions to be correct in that sense that no potential behavior is missed. And this you can do in a mathematical way. And the DO333 also gives a nice explanation what abstract interpretation is. So now we have looked at different kinds of static analysis, so let's get back again to the verification goals we want to address and how it really works. Like for example the stack usage. So if you take a look at the stack, well, and I mean the runtime stack here, so this is something which basically happens during program execution. So every procedure, every function you execute puts a frame on the stack, and inside this frame stack usage can grow depending on how registers are used, how variables are allocated. And if you run out of stack, you can trigger a stack overflow, and that severe errors, when they happen, they are typically hard to detect. They can cause crashes or invalid erroneous behavior, and they are really hard to find out whether some defect you're looking at is really a stack overflow. And the idea of abstract interpretation-based static analysis is basically to prove that you can never have such a stack overflow. And well, this is a static analysis, but here in this case the static analysis works at the executable code level. So we start at a fully linked executable. You can specify entry points, like you want to analyze the task or interrupt service routines, and then the static analysis kicks off and basically computes the worst case path through the software with respect to the stack heat. And this of course also gives the maximum stack usage of each task, of each interrupt service routine. And then you can also specify basically the interactions between the different tasks or ISRs, so you can derive the system level maximum. And the reason to start at the executable, of course, is that compilers and linkers have lots of leeway to generate the code, to optimize the code. Register allocation matters. So if you want to have a safe result, you need to start at this level. All right, then let's have a look at timing behavior. Well, this of course is relevant for real-time system where the correctness depends on the correct timing behavior, the correct temporal behavior. So that means if you have a real-time task, it must terminate before its deadline. And the corresponding requirements you'll find in all the standards. This is an example from the ISO 26262. And when talking about execution time, it's necessary to distinguish between the worst case execution time. So, so that means you have a piece of code, a task or an interrupt service routine, and you want to know how long the instructions of this task or interrupt service routine need to execute on this particular hardware. And then, if you have a multitasking system, it can be that this task is preempted or blocked. So the worst case response time then is the worst case execution time plus the time where the tasks are preempted or blocked. All right, so our contribution to this is at the worst case execution time level. So again, we want to analyze individual tasks, individual interrupt service routines. And you can see that the workflow is very similar to the stack analyzer I've shown before. So again, we are starting at the executable, specify the entry points or the task or interrupt service routine. You can say go, and then the analysis runs, computes a worst case path, this time with respect to the execution time. So we get an upper bound on the maximal worst case execution time here. And the core of the analysis is basically a microarchitectural model. So we have a model of the processor including caches pipelines. So we know how each instruction changes the cache, changes the pipeline, and then can do a cycle-wise evolution, how instructions travel through the pipeline, and also take into account all different possibilities or hardware states during the analysis. So I've mentioned that this works for timing predictable processors, which also include some multi-core processors like the Infineon Oryx, for example. But if you go for high performance multi-cores, then the system is not entirely timing predictable anymore, essentially because you have contention on shared resources like memories, caches, and also small elements like prefetch buffers and so on. There can be many of them. And then there is also the interconnect, the coherence fabrics of the bus systems. So access to the bus are subject to delays. They can be reordered. Sometimes they are undocumented, might be unbounded. So it's not reasonable to try to do a static model for this. And if you look at the guidance documents from EASA or FAA, AMC 2193, they give an overview of the necessary steps you have to take. Essentially, you have to basically identify the interference channels you have, develop a concept to mitigate them, and of course verify the timing behavior. And then either you can have a complete separation, so robust and time resource partitioning, or you need to determine worst case execution time for all the software components on all cores in the final configuration. And this is pretty much the setting for which we have the time weaver tool. So here the idea is again to compute a worst case execution time bound, this time for non-timing predictable processors. And to take this into account, basically it means that we do not do a static model of the architecture here, but we use instruction level traces. And what's very important here is that these traces should be non-intrusive, so no instrumentation needed, because of course instrumentation would change the timing behavior of the program again. And happily many of these processors offer such non-invasive trace interfaces we can just use. And then the analysis runs in a similar way like we have seen on the tools before. We take the starting point of a task executable, compute the call and control flow graph, then the analysis runs and computes the longest path. And this time the timing information is extracted from the trace information we have. Additional information here is, let's say, feedback about the trace coverage. So whether you have already achieved a good trace coverage or you should improve it, and also the time variance, because these traces here, of course, will reflect the interference you have between different cores, which can also be an interesting information. Now going back to DO 178C, with what we've seen so far, we can already discharge quite some elements of this objective accuracy and consistency I've shown before. But some stuff is still missing. So now let's have a look at this. And this is basically where R3 contributes. This is our abstract interpretation-based runtime error analysis tools. And here the goal is to look at the source code, so the C or C++ code, and detect all possible runtime errors. And here runtime errors are of course defined with respect to the programming language. So it's defects due to undefined or unspecified behaviors of the programming language. And that includes all the usual suspects like array index out of bounds, division by zero, buffer overflows, null pointers, dangling pointers, but also concurrency defects like data races, lock-unlock problems, or deadlocks. So they are all covered by this sound analysis. So R3 can guarantee that every possible data race is reported, or can basically report freedom of data races. So in other words, it means that if you do this, well, actually you have shown memory safety at the C or C++ level. If you can demonstrate that no undefined behavior is in the code, well, then the program will be memory safe. Side effects are that you can also do data and control flow analysis and also talk about the interactions, the interference between software components with data and control coupling analysis. And you can do more advanced analysis with R3, like for example a non-interference analysis by tainting, which can be applied to do a signal flow analysis, so independence of signals, or freedom of interference between software components. Well, then checking coding guidelines obviously is also covered, so the usual coding guidelines can be handled. And if you're in the automotive or avionics domain, then the usual operating system norms are automatically covered, so R3 knows what will happen in the operating system and can take into account automatically. with respect to data and control flow analysis, what does it mean? Well, control flow analysis is clear. You want to know which functions call which other functions. You want to know the call graph, possibly over all threads, or specifically one call graph per thread. In data flow analysis, the question is where you have access to variables, to which variables, at which location, function, thread. Is it a read-write access? Is it a thread local access? Is it a shared access? Or possibly even an access which is subject to a data race. So all this is covered by the data and control flow analysis. And of course, you can also detect unexpected data and control flow like this. And the soundness here is a very important point, because it means that no data or control flow is missed, because S3 will automatically track all accesses through pointers, be it data pointers or function pointers. And if you don't have soundness, you don't have this property, so there might always be some data and control flow which is missed. Now let's take a brief look at the non-interference analysis I mentioned. So one application here is signal flow analysis. This is quite interesting. It's required by upcoming legislation in California. And basically it means that there must be onboard monitoring devices for all signals which can influence the exhaust behavior. And you can only omit these onboard OBD devices if you can show that a certain signal does not have an impact on exhaust control. And exactly such interference between signals is something you can show with S3. So basically you can taint, you can color certain input signals. S3 will automatically track how these colors can propagate through the program. And if they don't arrive at the particular output signal, you have proof of non-interference, so that input signal cannot affect this particular output signal. You can use the same technique also to talk about, let's say, interference between software components, and also to talk about cybersecurities, like if you have a separation between trusted or untrusted code and data. Okay, and if you take all of this together, we can see that we are already in pretty good shape with respect to this particular verification objective here. So most of the requirements are highlighted are all satisfied. So that means when talking about return on investment of static analysis tools, one clear element, if you're in a safety system, is that, well, you discharge verification objectives of the relevant norms. And taken all together, this would be the overview of DO 178 or DO 330. So you can see different objectives where worst case execution time, worst case stack usage, or runtime error analysis, code guideline checking can contribute. The green things here are direct contributions, and the blue ones show where the tool results can be used to discharge higher level objectives. And you can see that it's quite a number of objectives to which this is relevant. Now let's have a look at different use cases of S3. So of course, one aspect is just to report quality measures. You can do code guideline checking. You can do safety or cybersecurity analysis, signal flow analysis. So basically that's lots of different use cases. And coming back to cybersecurity again, well, the observation is that, well, actually, a lot of security vulnerabilities comes from undefined, unspecified behavior in the programming language. So just the things S3 detects. And well, the nice thing is that S3 can really prove their absence. So you can prove the absence of buffer overflows, which is already a pretty good cybersecurity property. And then the other elements I've discussed before, like the code guideline checking, data and control flow analysis, or impact analysis, that of course is relevant for cybersecurity properties, and there are also some specific detection plugins built in directly in S3, like for example to detect spectral vulnerabilities. So I've talked about the safety norms. We have seen, okay, there is a direct contribution to security norms as well. And not surprisingly, if you look at DO 356A, which is about security assurance for avionics systems, basically to protect airworthiness from unintended, unauthorized electronic interactions. So basically, security assurance has to be performed, and the corresponding verification objectives are listed here. So here in this group, we have objectives which are really specific for the security process. Here we have objectives which might be shared with the safety process. And you can see that there are requirements like vulnerabilities in security measures have to be identified, which needs to assess bugs or weaknesses, whether they really constitute a vulnerability, which means, of course, you have to find them. So this is where Astray contributes. We have here refutation analysis, so you have to show the absence of bad behavior to identify vulnerabilities. So again, this is a topic which is addressed by Astray. Code guideline checking, as mentioned. Compliance to security requirements, like, for example, no unauthorized access. So you can see also to these objectives, static analysis tools can contribute. So in a regulated environment, this is pretty clear. What's interesting is that you will find also this in the CAA, which applies to any kind of digital product. So it applies basically to products which are not already regulated, like avionics, automotive, or medical. But all other products with digital elements, and you find requirements there. Well, products with digital elements shall be delivered without any known exploitable vulnerabilities. So that means, okay, this is really something you don't need just for safety or security critical systems. It's something to be considered for all kinds of digital connected systems. Right. So the next question is, okay, we have talked about safety, security, general software quality, what static analysis is. Now the question is how you can execute it. And well, of course, there are nice graphical user interfaces. You can click through the findings. But in the end, a big advantage of static analysis is that you can easily automate it. It's just something running on the source code, so you don't need to have some physical system running where you have to inject tests. You can just run, analyze the code offline whenever you like. And so the idea is to put all the sources and the analysis configuration in version control. You can automatically trigger analysis at an interval you like. This is just for the example of Astray, but would also apply to stack or worst case execution time analysis. So you can run the analysis automatically, just write out results, which you then commit back to version control, or have users, developers investigate the findings, possibly fix them, possibly interact with the analyzer, for example, by commenting alarms or fixing the code and committing back to version control. So this would be the general flow, how this can be used. To corroborate this, there are several ways to integrate the tools in the development process. So there is a Visual Studio Code plugin for Astray, which supports any kind of editor supporting the LSP protocol. There are Jenkins plugins, and there are integration in other IDEs and also into model-based development environments. Okay, so that's essentially the workflow. And now if we are looking back at regulated systems, then of course the question of tool qualification comes into play. And here what we can do is to offer qualification support kits, and that's basically elements which help you demonstrate that the tool works correctly in the operational context where the tool is applied. So that means essentially it's a validation suite with all corresponding reports, like for example the operational requirements of the tool, a verification test plan, a description of the test cases, and a scripting system to automatically execute the validation suite. So you can basically demonstrate that the tool runs okay in your particular installation of the tool. Then there are additional information about the tool development process. So essentially we can demonstrate compliance to safety norms in the tool development. And this is enough to do an automatic tool qualification to the highest criticality levels. So in ISO 26262 it would be up to ASLD TCL3. And this is the table from DO 178C. So for verification tools you have typically TQL 4 or 5, mostly TQL 5, and this is something you can support with the qualification kit. Okay, now let's get back again to the question of software defects and what really the benefit is now. And so this is just some numbers you can derive from the public reporting about the Toyota unintended acceleration case. So you'll find that, well, the portion of code NASA analyzed with respect to this incident covered about 280,000 lines of code. And you'll also find numbers what the recall costs were and estimations what the total cost of this defect was. And then an interesting thing you can do is to basically calculate this down to a particular line of code. And then you'll find that, well, if you look at the recall cost or the total cost, either in an optimistic or less optimistic way, well, then the cost per line of code ranges somehow between $7,000 and $17,000, which is quite expensive code. So that means if you have this kind of cost, it's probably a very good idea to just use some tools to avoid this cost and make each line of code a bit cheaper. This is also coming back to the slide we have before. This is also something you can see in this table here. And the interesting thing is that many of these cases which are listed here are actually cases where static analysis, as we have discussed it before, could at least contribute to identify the problem. So it includes the unintended acceleration problem of Toyota, which was the essential trigger was a stack overflow, but they had also other source code level defects. The Theorac incident, the Ariane explosion, Petrel missile problem, they were also related to runtime errors. Shutdown of the Yorktown destroyer was a division by 0. So that means these kinds of errors, which are amenable to static analysis, is something you really find also in the very expensive defects. So that means it's a technique which can be widely used, which can prevent critical issues from happening. And so, well, it's actually a very good idea to actually use them. Okay, so then I'm already at the end of basically my slide presentation. Just a brief conclusion. So I hope I could convince you that static analysis enables defect prevention and does it in an effective and efficient way. And if you then even use the abstract interpretation, the sound version of static analysis, well, then you can really maximize defect removal efficiency because you can prove essentially that you have gotten rid of all these defects. So the return on investment, actually it's quite a lot. So on the negative side you have this, so you can avoid lawsuits, accidents, recalls, and lower development, maintenance, and customer support costs. Positively formulated, well, you can shorten development cycles, you can improve the efficiency of development because the earlier you find defects, the less costly it is to repair them. Of course, you can improve software quality, you can ensure functional safety and cybersecurity, also availability. And then in the end, for any kind of systems, you can improve customer satisfaction and in the end increase the market share. So then I would like to conclude again with the statement of the book I've cited before a couple of times, that, well, the return on investment of static analysis tools really is higher than for basically all other defect detection methods which are around. And then I'm really at the end of my presentation, and would like to thank you for your participation.